Okay, we're going to go ahead and start off with this 2.7 homework. This is one of the more challenging sections of the entire class, so let's see how this works out. So we have each side of a square is increasing at a rate of 5 centimeters per second. At what rate is the area of the square increasing when the area is 81 square centimeters? So let me try and let's see where I want to do this. Let me try it in here and see how this works out. So there are two pictures I'm going to draw. Okay, one of them is what I call the general picture, and then the other one is for the instant in time. Okay, so the general picture is that we have a square. That means all sides are the same. And the square is changing. Each side is increasing at a rate of 5 centimeters per second. So since this square has a side that's changing, I will assign a variable to it, x. And of course, that means all the other sides are also x. Now, in the instant in question right here, we want to know how quick it was changing when the area of this thing is 81. Well, 81 square centimeters. Well, if the area is 81, that means since it's a square, each of these sides has to be 9. So that's the instant in question. When the sides are 9, at that instant, how quickly, at what rate is the area of the square increasing? So I'm going to go back to my general picture and make sure I have assigned variables here. Look at my instant picture. I know what the variable is, right? At that point in time, x is going to be 9. And then now I'm going to write down what I'm given and what I want in the problem. So what am I given and what is it that I want? Well, I'm given, first of all, a rate. Okay, that's the key thing. A rate is a derivative, and the rate is 5 centimeters per second. But what is the rate? What is that a rate of? So it's the rate that each side of the square is increasing. Well, the side I've called x. So what I know is that the rate of change of x with respect to time is 5 centimeters per second. What I want to know is the rate the area is increasing. So I want to know a rate, which means it's a derivative of what? The area. So I want the derivative of the area with respect to time. That's what I want to know, and I want it at a specific time, or at a specific point. I want it at exactly the moment that x was 9, and that's because I knew the area was 81. That meant x was 9. So now what I need to do, once I've written down what I'm given and what I want, is I would need to find an equation that relates x and a together. Well, coming back to my general picture over here, I have a square, and the area of that square is always going to be x squared. And that is an equation that has a in it and x in it, which is what I need. So I'll write down here a is equal to x squared. And at this point, I will differentiate this with respect to time. So I always like to draw a little squiggly because it's really implicit differentiation. I'm taking the derivative of each side. The derivative of a with respect to time is just dA dt. And then equals, now the derivative of x squared we have to be a little careful with. Derivative of x squared is 2x, that's the power rule. But then you have to say times the derivative of what's inside. Now normally the derivative of x has always been 1, but that's because we've been differentiating with respect to x. This time we're differentiating with respect to time, so we will have dx dt. So that's it. We finished off the power rule on the right side, right? The 2 came down, and then we took derivative of what was inside, which is like chain rule. And now what you'll see is that dA dt, right? dA dt, which is what we want, appears in our equation. Dx dt appears in our equation, and that's what we're given. And then we also have in here x, but we know at the instant in time what x is. Notice what I didn't do. I did not replace this x up here with 9 before I differentiated, because of course 9 squared would be 81, and then you would have derivative of 81 is 0. Well, the reason I do that is because if this square is changing, and then all of a sudden I say, okay, let's just make it a 9 by 9 square, then it's not changing anymore, and therefore you can't talk about rate of change of something. It's already stopped moving. So what we have to do is we have to find the general equation, don't fix any of the variables, differentiate that first, and then come in after the differentiation and fix the variables. So now let me rewrite this. dA dt is the right side. That's what I want to know. Equals x, 2 times x, but we know x is 9 centimeters. And then times dx dt, which is 5 centimeters per second. And therefore, you can start doing your units here. Centimeter times centimeter, centimeter squared divided by seconds. So we know that this is going to be equal to centimeters squared per second. And then just multiply here. 9 times 5 gives me 45 times 2 is 90. So I get 90 square centimeters per second. Now, I will point out that I usually don't pay attention to the units here. I usually just would write 2 times 9 times 5, and that would have given me 90. And then when I try and figure out what the units are, I look at the unit here. A here is area. Area is always measured in squared units, and I've been given centimeters, so I'll put centimeters squared. And then I have time here, and in this problem, time is measured in seconds, so I would say divided by seconds. So I get the same answer as I do here, but not worrying about the units until the end. All right. Now I know for a fact that their solution of this is not going to be anywhere near that much detail. Yeah. So, it is what it is. All right, next problem. The length of a rectangle is increasing at a rate of 5 centimeters per second, and its width is increasing at a rate of 7 centimeters per second. When the length is 7 centimeters and the width is 5 centimeters, how fast is the area of the rectangle increasing? So, again, here are my two pictures. I have my general picture, and then I have my instant in time. My general picture is a rectangle, not a square this time. And it's the length and the width are changing. So I'll call this side length, I'll call this side width. Now in my instant in time rectangle, I know that my length is 7 and my width is 5. Now, I need to look at a little the things that I want. It's never wrong to kind of write things as you think them. I mean, I'm just thinking, okay, what am I given in the problem? Well, I'm given that the length of the rectangle is increasing at a rate derivative, right? Derivative of the length at 5 centimeters per second. So I know that the dl dt, change in length with respect to time, is 5. I won't put centimeters per second. We'll know that that's what the unit is. And I'm also given that the width is increasing at a rate of 7 centimeters per second. So I know width is W here. So dW dt is 7. That's what I'm given. And then I would like to know how fast is a rate, how fast the area of the rectangle is increasing. So what I want to know is dA dt at exactly the moment that the length, when the length is 7 and the width is 5, is exactly the moment in time we're talking about. So when the length is 7 and the width is 5. So that's this picture here. Oh, Geez, jumped around on me there. Delete that. Okay, so I'm going to come back over here. Let me see. I need to find an equation that relates the length to the area, and the width to the area, because I have in my differentials there, I have L, W, and A. So come back to our general picture. Well, I know that the area of a rectangle is length times width, so I'll just write LW. And now what I need to do is differentiate that. So I'm going to clear out some space up here for myself. Ooh, I don't know how this is going to work. Cut that out. Might have been easier just to do that. Okay, so now I'm going to take that equation, which was A equals LW, and I'm going to differentiate it with respect to time. So on the left side, derivative of A with respect to time is dA dt. And on the right side, notice we have a product, so we must apply the product rule. The product rule says we take the derivative of the first one, which will, with respect to time, so the derivative of L with respect to time, then times product rule says just times the other one, no derivative, then plus the derivative of the other one, so derivative of W with respect to time, and then times the first one, which was L. And that is my product rule on the right-hand side. So let's just check some things here. dA dt, that's what I want. dL dt, I'm given. dW dt, I'm given. W, I know W at the instant in time, and L, I know at the instant in time. So I should be able to just plug everything in and get an answer here. So all of this will become dA dt, which I don't know, I'm trying to figure that out, equals dL dt, which was 5, times W, which was 5 at that instant in time, plus dW dt, which is 7, times L, which is also 7. So you get 25 plus 49, which is 74. So dA dt is 74. Now watch how I'm going to get these units. Area in this problem, the area, let's see, my units were centimeters, and area is squared units. So I'm going to put centimeters squared per. Now the time in the problem, time is measured in seconds. So I put per second. So 74 centimeters per second is the rate at which the area is increasing. Now again, do we want to see how little they show us? Yeah, that's it. Okay. Where am I? Okay, a cylindrical tank with radius 7 is being filled with water at a rate of 3 cubic meters per minute. I am making sure real quick that all my units are the same. So meters here, meters here. Sometimes they'll try and trick you and they'll make one of them centimeters or something just to see if you're going to convert. How fast is the height of the water increasing? All right, I think we should draw a picture. So what I'm going to do is I'm going to draw my picture here. I have my general. I'm just going to put G for general and I for instant. I have a cylindrical tank. Looks like this, a right cylinder. I'm going to have the same thing over here. Okay, now going back, cylindrical tank, radius is 7 meters. That's not going to change, okay, in both pictures, 7 meters, because the radius is not changing, right? It just says that you've got a radius 7 meters, that's it. Well, this cylinder is being filled with water at a rate of 3 cubic meters per minute. how fast is the height of the water increasing. So it doesn't give me an instant time. This is interesting. So we have water right in here, and the water is going in, right? Water is going in. And in this picture, yes, the water is going in, but they don't tell me like an instant in time. And I wonder if did they mess up? What's going on here? Well, maybe we should just write down what we're given. And maybe we should just write down what we want. So we're given something, we want something. Well, what are we given? We're given the radius. We already have that in our picture, but we're also given the rate at which the water is going in. The rate at which the water is going in is 3 cubic meters per minute. Cubic units is a measurement of volume, right? Square meters or square units is area, and then just meters by itself would just be length. So we have volume. They're giving us a rate at which the volume is changing. So what I need to do is back here, I need to realize that I'm given the rate of change of volume with respect to time, and that is 3. Was it 3? I'm tired. It's almost 1 o'clock in the morning. Yes, it was 3. What I want is to know how fast the height of the water is increasing. So I don't have a picture of my height of the water. I have not included that. So why don't I call this H? Now in my picture over here, I had my water. They don't tell me a specific instant, right? Well, I'll have to address that. But I want to know how fast H is changing, the rate at which H is changing with respect to time. So I need dH dt. And at what point in time or when do I want it? I don't even know. Well, does it even matter? Let's see. Do I need this at all? Let's just try and make a connection between the volume and the height. So when you have a right cylinder like this, you can look this up somewhere if you need to. The volume, I'm coming up with my equation. The volume is pi r squared times height. Now what I'm trying to do is find the volume of the water, not the cylinder itself. So that's why I used height here, right there. So that's the volume of the water inside the cylinder. And I know my radius. My radius is fixed, right? So volume will be, when I square r is 7. So 7 squared is 49. So this is 49 pi. I put the constant out front, and then I have the h there. That's my equation. I should have done this instead. Now, this is the thing I want to try and differentiate. So what's the derivative of the left? dv dt. And then on the right, 49 pi is a constant. So I just write 49 pi. Then times the derivative of h. Well, derivative of h with respect to time is dh dt. Now, notice, dh dt appears in my equation, and that's what I want. And dv dt appears in my equation, and that's what I'm given up here. And there's nothing else I need, right? Not at all. So what I can do is I can replace the left side, dv dt, with 3. And then on the right side, I have 49 pi. And then times dh dt. And now divide both sides by 49 pi. I get 3 over 49 pi is equal to dh dt. Now the only thing left to do is to figure out what my units are. So I'm going to say dh dt is equal to, now height is measured in our units, but not squared or cubed, just our units. So height, in this problem, everything was in meters. So I will put here 3 over 49 pi meters, and then time here was measured in, I believe, minutes. Yeah, minutes. So it'll be meters per minute. Right there. That is the rate at which the height of the water is increasing. So that's really how fast it's coming up the side of the tank. in meters per minute. I can barely keep my eyes open. Now they get a decimal approximation, but there it is, 3/49 pi. All right, I'm not quite sure how many more of these I'm going to be able to do. It's been an exhausting weekend. All right. Next one. The radius of a sphere is increasing. So the radius of the sphere is changing. It's getting bigger, which means the sphere is getting bigger. The rate at which that radius is increasing is 4 millimeters per second. How fast is the volume increasing, the volume of the sphere increasing when the diameter is 80 millimeters? So I have millimeters here, I have millimeters here. I'm happy with that. They give me a diameter. Be careful there, not a radius. So let me try and get my picture going here. What the heck? There we go. All right, two pictures. My general, my instant. Sphere. Sphere's got a radius. Oh, I don't like that picture. There's my sphere. Three-dimensional. There's another one. Okay, so my radius is changing, right? So I'm going to come in here and I'm going to label this as my radius. Over here, in my fixed point in time, my radius is actually half of the diameter. And the diameter was 80 millimeters, so it's going to be 40. So 40 millimeters. That's my instant in time. I'm given the rate at which the radius is changing. So dr dt, that's how fast the radius was increasing, and it was, let's see, 4 millimeters per second. 4 millimeters per second. I would like to know, I want to know how fast the volume of the sphere is changing. So dV dt, volume. And I want to know exactly what that rate of change is at exactly the moment that the diameter is 80, but that's the same as saying when the radius is 40. So now I need to come up with an equation that relates my radius and my volume of my sphere together. So, if you don't know what these common formulas are, just go to Google, say volume sphere, 4/3 pi r cubed. But, if you don't know that right offhand, you can just go look it up. So I know my formula is 4/3, it's bad for, pi r cubed. And there's my equation that has my r and my v in it, and it's the volume of the sphere. So now I'm ready to differentiate with respect to time. So dV dt is equal to now 4/3 pi is a constant, 4/3 pi, and then times the derivative of the radius cubed. So power rule first, well, chain rule and power rule. So power rule, 3 comes down, r gets squared. Then times the derivative of what was inside. The derivative of what's inside is r. So now what's the derivative of r? Well, with respect to time, it's dr dt. So now we should have everything we need. dV dt, trying to find that. Let's see, 4/3 pi times 3, that's all constants. Radius squared, well, I know what the radius is. It's 40. I can plug in 40 now. And then dr dt, we're given as 4. So I need to compute, let me see, I see these 3's cancel. So I have 4 pi, I have 40 squared times dr dt was 4. So work that out. That is your dV/dt. And let's talk about the units. Volume is going to be our unit cubed, and it was meters, millimeters, what the hell is it? Millimeters. Millimeters. So I'm going to say millimeters cubed per time here was measured in seconds. So seconds. And let me see, I'm sure they're going to have the solution here as approximate decimal. So let's see here. There's the 4, there's the pi. See, they said half of 80, which is 40 squared times 4. There it is right there. Oh, they didn't even get a decimal. They just multiply out the constants and leave the pi there. So that's fine. All right, let's see what else I've got left here. I know this is a long assignment. So Snowball. That is going to take some working on. Let me just help you set this one up. I'll try and do it quickly. 2 pictures here. Snowball melts. A snowball is a sphere. Okay, we're back to another sphere. There's my snowball. There's my snowball. Snowball melts, so it's getting smaller, so that the surface area decreases at a rate. Surface area is getting smaller by this rate. That's a derivative then. The change in area, I'm going to say surface area. Okay, I'm going to use A for surface area with respect to time, is 5, but it's getting smaller, so I'm going to use negative 5. Find the rate at which the diameter gets smaller. Okay, so I want the D, I'm going to say capital D for diameter. I want to know that at exactly the moment that the diameter is 9 centimeters. And also I just double checked that my units were all the same. At the moment that the diameter is 9 centimeters. So what I need is a formula that relates area and diameter, surface area to diameter for a sphere. So again, if you don't know, I wonder if it had it right here. It's not there, but area 4 pi r squared. Yeah. I didn't feel very confident about having that right on the tip of my tongue, but I didn't want to look stupid and say it was wrong. But 4 pi r squared is what I was thinking. 4 pi r squared is our surface area. So I'm going to write down surface area using A for surface area, 4 pi r squared. And I should probably point out that in my instant in time picture, right, D was 9. Over here in my picture, D was just D, right? Well, the problem is that our formula has an R in it, not a D. So it's not technically correct to differentiate this right now, but we can get around that pretty easily because we know the relationship between a radius and diameter. We know that the diameter is always twice the radius. Or if you like, you could say take half of the diameter and that's your radius. So what I'm going to do is I'm going to take my formula, A equals 4 pi. I'm going to replace my radius with half the diameter and squared. Now I'm going to square it. So 4 pi, when I square 1/2, I get 1/4. When I square D, I get D squared. The 4's cancel, and what you're left with is A equals pi D squared, and that's our formula. We're going to differentiate this because I have A and D in it now instead of A and R. So derivative left side, dA dt equals pi as a constant. 2 comes out times D. So the 2 came out like power rule, right? The 2 came out like power rule, but then you have to do derivative of D itself. Oh, and I reduced the power, so there's a 1 up there. And then d dt. Separate that. So there's my derivative. Get that out of there. dA dt is given. D at the moment in time is given. dt is what I want to know. So I should be able to compute everything there. Replace this with -5, replace that with 9, work things out. So you have -5 over 18 pi. Check this one. And we should get a negative answer because it's decreasing. -5 over 18 pi right there. Oh, hey, they gave you a picture. Seems odd that they would go out of their way to show you a picture for that one. And then our units, of course, we could use the same argument, centimeters per minute. Area is measured in, oh wait, no, we want dt. So diameter is measured in centimeters, so it'll be centimeters per minute. Okay, I think that's all I've got energy for tonight. There's still a lot more that has to be done here. These problems are significantly different. So you just have to give me some more time to get to those. I may or may not be able to do it by the time it's due. So I think what I'm going to do is maybe just push an extension of 1 day on 2.7. All right.